And good morning, everybody. I'm hoping my audio is on. Looks like it is. I am recording a short video. This is for both my Monday, Wednesday, and Tuesday, Thursday class. Monday, Wednesday, you had Jerry Wright substituting for me while I was away. It sounds like he had a good time. I hope you all did too. And for my Tuesday, Thursday class, I got pretty flustered while I was going over this, and I've made some adaptations to the in-class activity we did yesterday. And I just want to tell all of you about it if you're interested. So if you want to click, it is open. It's on Wednesday the 19th for the Monday, Wednesday class, Thursday the 20th for the Tuesday, Thursday. But I've updated this and changed the questions a little bit. Okay. So just to remind you, let me bring this up real large. The class started with this warm up just to remind you about the writing of exponential equations, both decay and growth. So you came up with equations for a 2% growth rate of 60 rabbits, which comes up again in the in-class problems. And then I wrote this other one to give you some experience with exponential decay, really noticing that both these things, if you think of one as nothing, multiplying by one has no effect, multiplying by numbers above one will be growth and below one will be decay. So when you see like a 2% growth, think of that as adding that 2% or 0.02 to 1. And when you think about decay, think about subtracting that 0.008 away from 1 to come up with the number that appears in the equation. And we went over a little bit. I guess Jerry did this on a graph, but real quick, I put in a reminder of how to do this. We're using logarithms. Okay, jumping to the meat of the point. I think what I didn't like about this problem, and I've changed for next time, is this whole thing is about changing the midline. And I basically wrote an effective equation in order to make this work, but it didn't focus on the midline before, and I've changed it to make it focus on the midline. So this one wasn't as big of a problem for either class, but just to go over the change of solution, what I instead did, I had this as a sort of an adjusted cosine up 50 to make this work. But I think it'd be more effective to think of just as the general cosine wave looking like this, above and below 50, that fluctuation of 50 rabbits. But that does require you, when you think about your base function of 60 rabbits growing at 2%, the 60 times 1.02 to the t, remembering that puts that 60 is at the bottom of your curve. So the midline isn't actually 60. The midline's at 60 plus 50, or starts at 110. So then I've also included this graph that does a little bit more of a job showing that midline. There's our start at 60 rabbits, and the midline started at 110 and then increasing exponentially over time, and having this nice yearly fluctuation based on the time of year in every cycle. All right. So the level 2 problem, I think, was written poorly, and it sounds like it went okay with Jerry. I definitely thought, oh, the wording does not make sense. So I actually changed level 2 to be a little simpler, just to say, modify your equation. And I didn't really point out the equation. The equation is essentially your fluctuation. You're using a cosine plus your exponential growth formula, which would be negative 50 cosine of pi over 6 times t, plus 60 times 1.02 to the t, plus that 50 to bring that midline up to where it should be. Okay, so this is all going to come back. I basically made it simpler and said just modify your equation so that the amplitude increases by 1% per year. So if you look at this last graph, the amplitude stays the same. It's always plus and minus 50, plus and minus 50. But the reality is if you have larger populations, there's probably a larger amount of fluctuation as well. So adding on this additional piece that the amplitude is increasing is a pretty simple add. You'll notice that if you multiply an exponential equation by a trigonometric or sinusoidal equation, then that will have that effect. So what we're showing here is this, just in order to change that, to have that added growth, if we just throw in this 1.01 to the power of t, and when it multiplies by that negative 50, it makes that 50 become a little bigger and a little bigger and a little bigger over time. Everything else about that equation is the same. And you can see the effect over 30 something months over about 3 years, you can see the amplitude getting bigger and bigger. And if we just replace our f of t, our fluctuation function, oh, I think I called that b of t. It should be f of t, the fluctuation. I'll change that and update it. Then really this is exactly the same as the first equation, except the only thing that's changed, it has that 1.01 in there. And you can see the effect it has where these waves above and below the midline are getting bigger and bigger and bigger as the amplitude increases over time. So what I really wanted to touch on this is we can start to get more accurate in our real world modeling by adding these little pieces, piece by piece. And I think I went a little above and beyond what 7.4 actually gets into. But I think I was also just excited about, the opportunity that this all presents. And I wanted to include it all in one story problem about the population of rabbits. So anyway, I think the lesson is improved and for the next group, and hopefully this cleared up any confusion that I left you with yesterday. Thanks for tuning in. I'll see you all next week.